Welcome all. In this lecture, we will discuss about the time evolution of the wave packet. And this lecture is from the textbook of Quantum Mechanics Concepts and Application by N. Jetili. So, before the discussion, let us look at the mathematical expression of the wave packet once again. So, I'm just showing you what is the mathematical expression for the wave packet. So you just look at this equation 1.94. This is psi xt is equal to 1 by root 2 pi minus infinity to plus infinity phi k e to the power I kx minus omega t into dk. And at t is equal to 0, we have to put t is equal to 0 here. So at that time t is equal to 0, the same packet is described in terms of psi 0x. We call it psi 0x, the left hand side, and that is equal to 1 by root 2 pi minus infinity to plus infinity phi k e to the power I kx dk. So phi k again can be Fourier transform and can be written in terms of psi 0x in equation 1.96. Later, we have shown that there was a term omega there, that in equation 1.95 in the expression of the wave packet there is a term omega. Now omega is a function of the wave number k, that is omega is equal to omega k, and this is true for the case of dispersive media. So if the omega is a function of omega k, then omega k can be expanded in Taylor series, which was given in equation 1.117. Actually, we have already discussed all these things in our previous lectures. So after expanding omega, the new form of the packet is this one, that is psi xt is equal to this one. This is expressed in equation 1.118. So after considering the Taylor expansion of omega, psi xt can be written in this fashion. So there are several terms here, as in Taylor's expansion there is the first term, second term, third term, and so on. So in psi xt, the new form of psi xt, there are several exponential terms. This one is the first term, this is the second term, and so on. Now let us come to the discussion again. So we need to decide on where to terminate the expansion. As we have already told that there is some Taylor expansion in omega k, but where we will terminate that expansion and what exponent term we will take as the integrand in the equation of psi xt. We are going to consider two separate cases corresponding to whether we terminate the exponent in at the linear term, that is k minus k0 vgt, or at the quadratic term k minus k0 whole square alpha t. So the point is that we are going to take two terms. The first term is k minus k0 vgt and the second term is k minus k0 whole square alpha t. These two cases are respectively known as the linear approximation and the quadratic approximation. So we are going to discuss two cases respectively. The first one is the linear approximation and the second one is the quadratic approximation. In the linear approximation, which is justified when g of k minus k0 is narrow enough to neglect the quadratic k square term. So when we can neglect quadratic k square term, at that time we can take the linear approximation. So we have to assume that k minus k0 whole square alpha t, k minus k0 whole square alpha t, that is very less than 1, and the wave packet which was just described in equation 1.118 that I have shown you a little bit earlier. So that equation now can be written in this way, that is psi xt is equal to 1 by root 2 pi e to the power I k0 x minus v phd minus infinity to plus infinity g of k minus k0 e to the power I into k minus k0 x minus vgt into dk. So we have only taken the linear term. Now equation 1.125 that can be written again in this way, that is we are writing psi xt is equal to e to the power I k0 x minus v phd into psi 0 x minus vgt into e to the power minus I k0 x minus vgt. In this way we can write this equation. So why we have written in this format? Because what was psi 0x that I have already shown you in the beginning of the lecture. There is an expression of psi 0x given in equation 1.95. So I request you to look at that equation again. So if psi 0x can be expressed in that way, then we can write this expression that is given in 1.125 in this fashion, that is psi 0 x minus vgt, because you see in the exponential term there is x minus vgt. So you can write psi 0 x minus vgt. Actually psi 0 x minus vgt is equal to 1 by root 2 pi minus infinity to plus infinity gq e to the power I x minus vgt into q plus I k0 x minus vgt dq. Actually in place of x there is x minus vgt, that is the difference from the equation given in 1.95. So in equation 1.95 if you write x minus vgt in place of x, then you can have this equation 1.127. Thus by incorporating the term psi 0 x minus vgt, we can rewrite the equation given in 1.125 by in this fashion. So this is the new expression of psi xt, and we have assumed that small q is equal to k minus k0. Here you see that there is dq. So and here is q. So what is q? Q is actually k minus k0. Now you see equation 1.126 again. So in the left hand side there is psi xt, and in the right hand side psi 0 x minus vgt has been multiplied with some exponential term which are complex number. So if you take the mod values, so we can say that mod of psi xt whole square is equal to mod of psi 0 x minus vgt whole square. So what is the meaning of equation 1.128? Equation 1.126 represents a wave packet whose amplitude is modulated. So what is equation 1.126? That represents a wave packet whose amplitude is modulated. As depicted in figure 1.14, as depicted in figure 1.14. So let us see figure 1.14 again. This is figure 1.14. So in figure 1.14, there is a modulating wave psi 0 x minus vgt propagates to the right with the group velocity vg. So there is a modulating wave psi 0 x minus vgt that is propagating to the right with the group velocity vg, and there is a modulated wave that is e to the power I k0 x minus v phd, and it represents a pure harmonic wave of constant wave number k0 that also travels to the right with the phase velocity vph. So I repeat it again. Actually equation 1.126 that can be plotted in this way, that there is a modulating wave. There are two types of wave. One is modulating wave, that is psi 0 x minus vgt, that is propagating to the right with the group velocity vg, and there is also a modulated wave, that is e to the power I k0 x minus v phd, that represents a pure harmonic waves of constant wave number k0 that also travels to the right with the phase velocity vph. That is equation 1.126 and equation 1.128 represent a wave packet whose peak travels as a whole with the velocity vg, while the individual wave propagates inside the envelope with the velocity vp. So we will look back figure 1.14 again. So you see that this dotted curve is actually the wave packet, and this packet moves with the velocity vg to the right side, and inside this packet or inside this envelope there are some waves that is also moving with velocity vph to the right side. So the group velocity, which gives the velocity of the packet speed. We have just described uh, the figure in figure 1.14. So you see there is an envelope of the figure which is the dotted curve, and the velocity of the packet's peak clearly represents the velocity of the particle. I am repeating the sentence again. This is very important, that we have just described that there is a wave packet, the dotted curve. That is the envelope actually, or that is the peak of the curve. So the group velocity, which gives the velocity of the packet's peak actually. What is the group velocity? Group velocity gives the velocity of the wave packet's peak, and it clearly represents the velocity of the particle. So group velocity represents the velocity of the particle. Since the chance of finding the particle around the packet's peak is much higher than finding it in any other region of space. This is also very important sentence, that is, the chance of finding the particle around the packet's peak is much higher than finding it in any other region of space. The wave packet is highly localized in the neighborhood of the particle's position and vanishes elsewhere. It is therefore the group velocity, not the phase velocity, that is equal to the velocity of the particle represented by the packet. So velocity of the particle is represented by the velocity of the peak of the wave packet. This suggests that the motion of a material particle can be described well by wave packets. So the motion of the material particle can be well described by wave packets. By establishing a correspondence between the particle's velocity and the velocity of the wave packet's peak, we see that the wave packet concept jointly embodies the particle aspect and the wave aspect of the material particles. This is also very important conclusion, because we are describing the motion of the material particle in terms of the wave packets and establishing a correspondence between the particle's velocity. Particle's velocity is a classical concept, and the velocity of the wave packet's peak. The wave packet is actually a quantum concept. So what we are doing, we are establishing a correspondence between a classical concept and a quantum concept. And we see that the wave packet concept jointly embodies the particle aspect as well as the wave aspect of the material particles. Now, what about the size of the wave packet in the linear approximation? Is it affected by the particle's propagation? That is one important question. That is, there must be some size of the wave packet, and is there any change in its size? Clearly not. This can be immediately, we can see from equation 1.126, that is psi 0 x minus vgt represents, mathematically speaking, a curve that travels to the right with a velocity vg without deformation. This means that if the packet is initially Gaussian, it will remain Gaussian as it propagates in space without any change in its size. So there will be no change in its size. To summarize, we have shown that in the linear approximation, the wave packet propagates undistorted and undergoes a uniform translational motion. So I am repeating it again. So if we use the linear approximation, so what we can observe? The first thing is that there will be modulation in the amplitude of the wave packet. So there will be a modulating wave, and there also will be a modulated wave. So what is modulating wave? The modulating wave is actually the wave packet whose peak travels as a whole with the velocity Vg, that is group velocity. And what is modulated wave? That is e to the power I k0 x minus v phd, that represents a pure harmonic wave of constant wave number k0 that also travels to the right with the phase velocity v ph. And another thing is that one important thing, that is when we are describe the motion of the particle in terms of the wave packet. So by establishing a correspondence between the particle's velocity and the velocity of the wave packet's peak, we see that the wave packet concept jointly embodies the particle aspect and the wave aspect of the material particle. And again we look at equation 1.126 again. So this is equation 1.126, and you also see that equation 1.128 that says that mod of psi xt whole square is equal to mod of psi 0 x minus vgt whole square. So what is the meaning of those equations? So psi 0 x minus vgt represents, mathematically speaking, a curve that travels to the right with a velocity vg without deformation. This means that if the packet is initially Gaussian, it will remain Gaussian as it propagates in space without any change in its size. But this is only true for the linear approximation of the omega k. Thank you all for listening the lecture.